Hey everybody, we're talking about polynomial functions of a higher degree. And up until this point where we've pretty much used linear and quadratic, but let me remind you what a degree is. And no, even though this is great and it is a very important type of degree, this is not the type of degree we're talking about. We're talking about the type of degree that we see by looking at the exponents on the terms of a polynomial. And so here's what it is. A degree is the largest exponent in a polynomial. So if a term has more than one variable, then you would add them, but only if there's more than one variable. So here's an example of that. Okay, so for example, the degree for 2x plus 1 is we're only going to look at this variable right here, which has that invisible exponent of 1, so our degree is 1. Same thing here. We're going to look at our invisible or compare our exponents. So we see exponents here at 2 and 1. So the degree is the biggest exponent on a single term. So here's a term, and here's a term. And technically this is 4, and if I want to put it in terms of x, it'd be x to the 0 power, because anything to the 0 power is just 1, okay? So when we see a constant term, there's really a degree of 0 on it. Anyway, so when we're looking at these exponents of 2, 1, or 0, we're going to look at the biggest one, and that's the degree. So let's look at this one. If I look at this term, and this term, again, this is really like saying x to the 0. We're going to compare those exponents. This is really an exponent of 1. And we've got a degree of 2 because it's the biggest. Again, this function here, there's 1, 2, 3 terms. This one is just a constant 4, so we know it's got a power of 0 on it. And again, we're going to compare the 3, the 2, and the 0. So the degree is 3 on that one. Again, here's our 2 terms. Degree is 3 on this one. Now here I see 1, 2, 3, 4, 5 terms. This is a degree of 0, so we compare all the exponents. And I see that the biggest one is 6, so we say that it's a degree of 6. Now, this is when it gets a little bit tricky. This is when we have more than one variable. You want to go through and make sure that we can see all the invisible exponents. And here's what we're looking at. Here's 1 term, 2 terms, 3 terms, and we're going to look at the degree on each term. So this exponent is 2. This exponent is 1. And this term has 2 exponents on that, which means that we add the 1 and the 2 exponents, which means it gives us a total degree of 3. So when there's more than one exponent, we say we add them on each term and we get a degree of 3. So hopefully that's a reminder to you. I know you've seen degrees before. So here's the other thing. Remember this parent functions paper that I gave you? We're going to kind of zoom in on this cubic function. Okay, so we need to know a couple of things about our cubic graph. And our cubic graph says that we look here and we see that it's from left to right, looks kind of like a snake a little bit, like it slithers. But our domain is from negative infinity to positive infinity. There's no restriction on the x values. Our range is the same because it goes all the way down to negative infinity and all the way up to positive infinity. Our x and y intercept is at 0, 0, so we just say the intercept for both is at 0, 0. And it's increasing everywhere, which means it's increasing from negative infinity to infinity. It's also an odd function because it's got that third exponent, and it has what's called origin symmetry. which means that it's symmetrical if you turn it on itself with, like, pretend like there's a spinner on that origin and we spun it 180 degrees. It's called origin symmetry. Okay, so today we're focusing on that cubic function a little bit more. So we're going to use what we've learned in our previous function and apply it for Mr. Cubic function. And it doesn't, I'm just having fun. It doesn't have to be a Mr. It could be a Miss or Mrs., whatever. So looking at this, we know that our cubic function looks like this. Okay. So if I'm going to see what this does to it, so this negative in front, remember, the negative in front is a vertical reflection across the x-axis. So that means, and I'm going to go ahead and put this one in purple, make it bigger. This means that when I graph g of x equals negative x cubed, it's going to be the exact same function that we had before, but instead, it's going to reflect across the x-axis. So that means our vertice is going to be the same, but instead of going up and to the right, it's going to go down and to the right. Instead of going down and to the left, it's going to go up and to the left. So that's our negative x cubed. Now we're going to look and see, okay, what's going on here with this one right here? Well, we know that that plus 1 outside of the x parentheses, we're going to say that's a vertical shift up 1 unit. So going from the black, again, our vertex is not, our center is not at 0, 0. We're going up 1, but then everything else stays the same. Okay, so that's our x cubed plus 1. And then I'm just going to go ahead and put the next one in orange. So we can see here, this one's going to be changed. Remember that horizontal changes are in the parentheses, or aka funky town. So we have a horizontal shift. Remember, everything's opposite of what we see. So it looks like a negative one, but it's really a positive one to the right. So from our black graph, we're going to go over to the right one, and we're going to have the same shape. Okay. So it's the same shape of our graph, but we're still using those transformations just like we were before when we were talking about our parabolas from chapter 1. Okay, now this is really cool. There's something for all polynomials called the leading coefficient test, or aka we can call this the end behavior test, where we can say, okay, let the A term be the coefficient on the leading term, meaning the highest degree. Okay, so we have this chart that we're going to use, okay? So, for example, let's just say we had y equals 2x cubed plus 2x, okay? What we'd be looking at here is the value of the leading coefficient on the highest term. So I know the degree of this polynomial is 3, which means we're going to be looking at this term right here. We're looking at the leading coefficient, which is a positive 2, okay? And it has a degree of 3. So we would call this a positive odd leading coefficient. So here's what we know about, and this was just an example. This chart that I'm giving you right now will help you see what's going on in every type of polynomial, okay? So these two columns here are for the leading coefficient. Either they're positive or negative. And this side over here is for the leading coefficient term, and we're just looking at the degree. So the degree will be either even or odd. Okay, and then these squiggly lines in the middle just mean we don't know what's happening on the middle of the graph. We just know what's happening in the end behaviors. So that's on your most left side and your most right side. So here's what we know. If it's positive, I'm going to put this one in green. If it's positive and even, if it's positive, it always ends up. So that's for the even and the odd. So if it's positive, It always ends up. Now, if it's an even degree, they match on each side, meaning even Steven, they match on each side. So on an even and positive graph, we see it's going up to the left and up to the right. Whereas on the odd positive, we know it goes up to the right because it's positive, but the odd functions are mismatched. They're opposites. So we go, for our odd positive, we go up to the right, but down to the left. All right, now let's look at even negatives. I'm going to use purple here. For negative functions, we always go down to the right. So that's for both of these. We always go down to the right. And remember, even, they match on each side. So if it goes down to the right, it's going to go also down to the left. But odd functions are mismatched, and this one's going to go up to the left. So again, the squiggly lines in the middle just means I don't know what's going on in the middle of our graph, but this just tells us what's happening on the left side and the right side. So the way that we would say this is we would say, as x approaches negative infinity, which means this way, right? F of x approaches positive infinity, which is the whole function, which is the left side. For the right side, we would say as x approaches infinity, so that's going this way, that's our x. Okay, as x approaches infinity, f of x is also approaching infinity. On the left side here, we would say as x approaches negative infinity, f of x is approaching also negative infinity because it's going down. And as x approaches positive infinity, we say f of x is also approaching negative infinity because it's also going down. For our odd positive, we would say for the left side that as x approaches negative infinity, which is the left, that f of x approaches infinity. And for the right side, as x approaches infinity, f of x also approaches infinity. And this one was negative infinity on the top. And then for the left side here, as x approaches negative infinity to the left, f of x is approaching positive infinity because it's going up. And for the right side, as x approaches positive infinity, f of x is approaching negative infinity because it's going down. So that might take a little bit of time for you to really comprehend that, but make sure you've got it written down and really think about it, okay? You should be able to reproduce at least the visual part of the graph anytime we're going to graph our polynomials, because it's really important that you're going to be able to do that quickly. So just keep in mind, positive graphs always go up and to the right, up and to the right. Even graphs match. So if it's positive even, it goes up and up. Negative graphs always go down and to the right. Even always matches. So if it's a negative even, it goes down and down. If it's odd positive, again, it ends up. So it starts the opposite. And negative graphs always end down. So if it's odd and negative, it is going to start up and end down that way to the right. So let's use what we just learned. So what is the right hand and left hand and behavior of f of x equals negative 3x cubed plus 4x? Now, when we're using that chart, I literally don't care about any other term except for this one right here, which is the biggest degree. So by this term, I can tell that our degree is 3. So that's an odd. And our leading coefficient is negative. So it's a negative odd. So when we look at our graph, let's go up here. Negative odd is going to be, here's our negative and here's our odd, and here's where we're looking. So we know that our graph will be, on the left side will be going up, and on the right side will be going down. So we say the degree is 3, which is odd. The leading coefficient is negative, so it's going to look like this. If it's negative, it ends down, and if it's odd, they mismatch. So on the left side, we're going up, and on the right side, we're going down. Or you can say, as x approaches negative infinity, f of x approaches infinity. And as x approaches infinity, f of x approaches negative infinity. Now let's talk about zeros of polynomial functions. So remember, zeros are where the polynomial cross the x-axis, right? So if f has a degree of n, so we'll just have it some number. We don't know what number it is. If f has a degree of n, it tells me two things about it. Number one, it says the function has at most the same number n zeros. So if it's to the 5th power, it has at most 5 zeros. If it's to the 3rd power, it's at most 3 zeros. And number two, f has at most n minus 1 relative extrema, or meaning maximum or minimum. So if we have a polynomial with a degree of 5, we have at most 5 zeros, and we have at most 5 minus 1, or 4 relative maximum or minimums. Okay, let's talk about what that looks like. So let's say here's our graph of f of x. Okay, we don't know what the function is, but here's what we do know. We see right here that it's crossing the x-axis at this value of x equals b. So we know that value of x equals b, we can call it a x-intercept. We could call it a 0. We could call it a solution, or we could call it a root. So remember, all 4 of those words are synonymous. And the other characteristic about it is that we know x minus that value of b, parentheses, is a factor of the function of f. Have you ever thought about that? That when we are taking a polynomial and factoring it down, when we set it equal to 0, it's always the opposite value of what we see. So we know that b is a x-intercept 0 solution and root, and we also know that x minus b is a factor of that function. So let's use that. So if we were to find all the zeros of f of x equals x cubed minus x squared minus 2x, here's how to do that. To find the 0 means you have to set it equal to 0. So that means instead of f of x, we want to know where it crosses the x-axis at 0, or the value of y equals 0. So we say 0 equals x cubed minus x squared minus 2x, and now we're just solving. I see here I could do a couple different things, but we're going to factor, and we're going to factor out an x. When I factor out the x, I get x squared minus x minus 2. And then once I'm looking at that, I have a couple of different options, but what I'm going to do is I can see that I can factor this down as well. It's a quadratic, and I can say, well, I know that x times x gives me x squared, and if we've got a negative 2 and a positive 1, that will get me back to x squared minus x minus 2. So here's all my factors. I'm putting them in parentheses. And remember our zero product property, that something times something equals 0 means that at least one of those things have to be 0, if not all of them. So we'll say x equals 0, x minus 2 equals 0, and x plus 1 equals 0. So this one's done. We'll just solve this one where we get x equals 2, and we'll solve this one so we get x equals negative 1. So those are all of our zeros, our real zeros, for x cubed minus x squared minus 2. And remember how we talked about if this is our biggest degree, then we have at maximum 3 zeros, which we just saw that there's 1, 2, 3 zeros here. Okay, so what if they asked you to find all the real zeros and relative extrema? So we're going to do the same thing to find the zeros. We're going to set it equal to 0 and solve that first. Factor where you can. I'm going to pull out a GCF of an x squared. Now I'm left with negative 2x squared plus 2. And actually, I could have pulled out a 2 as well, so hold on. And then this becomes a 1. And then, ooh, if I actually pulled out a negative 2 from both of them, this becomes a positive x squared minus a 1, which is x squared minus 1, which I know that this is a difference of 2 squares. So this becomes x minus 1, x plus 1, and that's a factor as well. Once we have that, our zeros are going to be 0, positive 1, and negative 1. Now, to find the relative extrema, we're going to have to graph it, which this is a picture of the graph. You could put this in your graphing calculator. So we can see that our x equals 0 right here, 1 right here, and negative 1 right here. So those are our values here, here, and here. But our relative extrema, or minimums, or maximums, we can see those little curves on the graph. I'll put them in red, is we see that there's a maximum here and a maximum here. So our relative maximums, we have a relative maximum of a value of 0.5 at x equals negative 0.71 right here. And we also have another one where it's a relative, whoops, that's a relative maximum of 0.5, which is always the y value, by the way. Maximums and minimums are always the y value at x equals positive 0.71. Okay, so to find the zeros, we set it equal to 0, but to find the relative maximums, for now, we're just going to look at the graphs. Okay, and then we're almost done. What if they give you the zeros and then you have to find the function that it could have come from? Now, there are a bunch of different functions that could have these same zeros, but we're going to find the most basic function that has zeros at -1/2, 3, and 3. So here's how you do it. We talked about if it has a 0 at a certain value, then it has factors of x minus those zeros or those roots. So I'm going to set this up first with x minus x minus x minus. And then I'm going to plug in whatever those roots are. So I'm going to go -1/2 here, positive 3 here, and positive 3 here. So remember that when you're putting it in the factors, it's always x minus. And then we're going to go ahead and simplify. So I'm going to FOIL these out. And when you FOIL, you can only do 2 at a time. So I'm going to do these 2 first. First, outer, inner, last, we get x squared minus 3x minus 3x plus 9, which is x squared minus 6x plus 9. And we're going to multiply it with x plus 1/2. So we're going to distribute it first all the way there. So we get x cubed minus 6x squared plus 9x, and then multiply 1/2 plus 1/2 x squared minus 3x plus 9 over 2. And then you're just going to combine your like terms, which we see there's like terms here, and we see like terms here. So we get f of x could be x cubed. -6 plus 1/2 is really -5.5 or 5.5x squared. 9x minus 3x is positive 6x plus 9/2. And that is one of the potential polynomial functions, but it's the most basic one. We could multiply this by any number to get all of the other possible functions as well, but this is our most basic. And then last but not least, here's how to sketch a graph of a polynomial. So there's 3 different steps we're going to take. We're going to look at the end behavior of the polynomial, which is that grid, right? So for example here, I know my biggest degree here is 4. So my degree is 4, and my a value is 3. So we know we have a even and positive leading coefficient test. So if it's even and positive, remember it goes up and to the right and it matches up and to the left. Then we find the zeros. So we know the zeros here will be 0 equals 3x to the 4th minus 4x cubed. We're going to factor. And we get this set equal to 0. So we have our answers are. Now remember, when x cubed equals 0, that means it hits what's called a multiplicity of 3, meaning x cubed means it hits that 0 essentially three different times. So we have a multiplicity of 3 at x equals 0. And then we also say 3x minus 4 equals 0 from right here. So we add the 4 to both sides. 3x equals 4. Divide both sides by 3. And we're left with x equals 4/3. So here's my roots. It happens once at 4/3 and a multiplicity of 3 at 0. Multiplicities of multiple numbers also tell you whether or not it goes through that value or it just bounces off. And if it has a multiplicity of an odd number, it goes through. And then the other thing is you want to find a couple of extra points just so we know where it's going. So for this one, I'm just going to pick some values that would go well here. So if I've got x and y, I'm going to pick some values of x, which is like, let's try -1. We'll try a half. We'll do 1 because 0 isn't helpful here because we already know the zeros. And we'll try 1.5. And if I plug those in the calculator, we're going to get 7, -0.31, which is fine. We're just graphing, -1, and 1.69. And then we're going to put that all together, all that information, and we're going to draw it out. And actually, I need my graph paper for this. Okay, so here's my graph paper. So first thing we're going to do is we're going to look at our zeros. So we have a 0 3 times at 0. So at that point, remember, it's going to go through that 0, and at 4/3. So let's call this a value of 1. So at 4/3, so that would be 4/3 is right here. If this is 2, it also has an x coordinate. We know that it has a degree of 4, so it's going to be even, and it's going to go up to the left and up to the right. So basically from these two values, it's going to go up to the right and up to the left, and then we have to figure out what's happening in the middle, which is why we did these values here, okay? So looking at this, we know it's at -1, 7. So actually, I'm going to kind of clean this up a little bit. At -1, it's up 7, so let's call this 7. So we know it looks like this. At 0.5, it's at -3.1, so half of the way it's at -0.31. At 1, it's at -1, if we call this -1. And at 1.5, it's at positive 1.5, so it's right here. It'll be like positive 1.69. So we're just going to kind of graph what we have here, and that's what it looks like. Something like that.